Subscribe to Dr. Khalkar's classroom channel and press the bell icon to get latest updates. Hello everyone, I hope you are doing great. In my previous lecture video, I have discussed about application of p-n junction, that is solar cell. In this lecture video, I will discuss about Hall effect. So let's get started. The content of this lecture video is as follows. First of all, I will discuss about Hall effect and Hall coefficient. Followed by I will explain about applications of Hall effect, and we will see some solved numericals based on the same theory. Hall effect. The Hall effect is the production of a voltage difference, which is called as a Hall voltage, across an electrical conductor transverse to an electric current in the conductor and to an applied magnetic field which is perpendicular to the current. It was discovered by Edwin Hall in 1879. This Hall voltage or Hall effect becomes observable in a perpendicular applied magnetic field across voltage contacts that lie on the boundary of the void on either side of a line connecting the current contacts. It exhibits apparent sign reversal in comparison to the standard ordinary Hall effect in the simply connected specimen. And this Hall effect depends on the current injected from within the void. The Hall coefficient is defined as the ratio of the induced electric field to the product of the current density and the applied magnetic field. It is a characteristic of the material from which the conductor is made, since its value depends on the type, number, and properties of charge carriers that constitute the current. The Hall effect is due to the nature of the current in a conductor. Current consists of the movement of many small charge carriers, typically electrons, holes, ions, or all these three. When a magnetic field is present, these charges experience a force called the Lorentz force. When such a magnetic field is absent, the charges follow approximately straight line of sight paths between collisions with the impurities, that is phonons, etc. Here please do not get confused between photon and phonon. A phonon is the quantum mechanical description of an elementary vibrational motion in which a lattice of atoms or molecules uniformly oscillates at a single frequency. Broadly speaking, phonon is a vibrational energy quantized in a packet. Phonons can be thought of as quantized sound waves similar to photons as quantized light waves. And the photon is a type of elementary particle. It is the quantum of the electromagnetic field, including electromagnetic radiation such as light and radio waves. And the force carrier for the electromagnetic force, photons are massless and they always move at speed of light in vacuum. So this is the difference between photon and phonon. So don't get confused between these two. However, when a magnetic field with a perpendicular component is applied, their paths between collisions are curved. Thus, moving charges accumulate on one face of the material. This leaves equal and opposite charges exposed on the other face, where there is a shortage of mobile charges. The result is an asymmetric distribution of charge density across the Hall element, arising from a force that is perpendicular both the line of sight path and the applied magnetic field. The separation of charge establishes an electric field that opposes the migration of further charge, so a steady electric potential is established for as long as the charge is flowing. Now let's see the explanation of Hall effect, in which Hall effect for different directions of electric current and magnetic field is shown in this figure number 1. In this figure, number 1 stands for electrons, 2 is Hall element, 3 is magnet, 4 is magnetic field, and phi-u is a power source. In drawing A, the Hall element takes on a negative charge at the top edge, which is shown in blue color, and the positive at the lower edge, which is shown in the red color. In figure B and C, either the electric current or the magnetic field is reversed, causing the polarization on reverse. Thereby, the reversing both current and magnetic field, which is drawing in figure D, causes the Hall element to again assume a negative charge at the upper edge. Now consider a slab of conductor or semiconductor as shown in this figure number 2. In this figure, let's consider small w is the width of the slab, small d is the thickness of the slab, capital I is the current flowing through the slab, small n charge concentration, small q charge on the carriers, small v subscript small d is the drift velocity of charge carriers, capital A is the cross-sectional area of the slab, capital F subscript capital L is the force due to the magnetic field, capital F subscript capital E is the force due to electric field, and capital V subscript capital H is nothing but the Hall voltage. Now let's say in this figure, let the electric current is flowing through a slab of conductor or semiconductor along its length. A magnetic field is applied to the slab perpendicular direction of the current flowing along its thickness. Due to the force of magnetic field, that is the Lorentz force, the charge carriers are deflected towards opposite edges of the slab. This generates electric field and develops potential difference across the edges of the slab, that is along the width of the slab. This electric field is perpendicular to the direction of flow of current and the magnetic field, which is shown here in this diagram. The Hall effect is demonstrated in this animated figure. Hall effect is a generation of a transverse electric field in a solid material when it carries an electric current and is placed in a magnetic field that is perpendicular to the current, which is I have already explained before. Charge carriers experiences a force known as Lorentz force, due to which charge carriers are deflected towards the edges of the slab. The deflected charge carriers results rise in a Hall voltage, which is shown here in this animated figure. Now let's consider the cross-sectional area of the semiconductor. Let's say capital A is equal to WD. The current through the semiconductor capital I is equal to NQAVD. Hence, Vd, that is the drift velocity, is equal to I upon NQA. Let's say this is equation number 1. Now let's see the force due to magnetic field. Due to current I, electrons moving along the length of the solid. When magnetic field of strength capital B is applied perpendicular along the thickness of the slab, charge carriers experiences a force known as a Lorentz force. Due to this Lorentz force, charge carriers are deflected towards the edges of the slab. The magnitude of the force is given by capital F subscript capital L is equal to BQVD. Let's say this is equation number 2. Charge carriers are now concentrated along the edges of the slab. Thus, an electric field created along the edges of the slab, let's say capital E subscript capital H. Now let's see the force due to electric field. Electric field developed across the edges of EH exerts an attractive force on the charge carriers. It exerts a force on charge carriers in opposite direction. Force due to electric field on the charge carriers is given by Fe is equal to QEH. Let's say this is equation number 3. Under the equilibrium of forces due to magnetic and electric field, charge carriers are under the influence of these two forces. One force due to magnetic field, that is FL, and second due to the electric field, that is Fe. Both forces are in opposite direction. Under the equilibrium, if magnitude of both forces is equal and net force on charge carrier is 0, thus we can write FL is equal to Fe. Now substituting the values from equation number 2 and equation number 3, we can write capital B into QVD is equal to Q into EH. Therefore, simplifying this equation, we can write EH is equal to BVD. Let's say this is equation number 4. If VH is the potential difference generated along the width of the slab due to the electric field EH, then we can write above equation EH is equal to VH upon W. Therefore, putting the value of EH in equation number 4, we can write VH upon W is equal to B into VD. By rearranging this equation, we can write VH is equal to B into VD into W. As we know that VD, that is the drift velocity, is equal to capital I, that is the current, divided by NQWD. Therefore, the potential VH, we can write VH is equal to B into I upon NQWD into W. So by simplification of this equation, we can write VH is equal to BI upon NQD. Let's say this is equation number 5. Therefore, rearranging this equation, we can write VH is equal to 1 upon NQ into BI upon D. So simply rearranging these all parameters, we have this equation number 6. Therefore, the quantity in this equation RH is equal to 1 upon NQ. This quantity is known as a Hall coefficient. Thus, Hall voltage is given by VH is equal to RH into BI upon D. Let's say this is equation number 7. Hence, magnitude and the direction of Hall voltage is dependent on magnitude and direction of current and magnetic field. Also, Hall voltage is inversely proportional to the thickness of the slab, which is shown from equation number 7. Now let's see the determination of type of semiconductor. The Hall voltage developed across the edges of the semiconductor is written as VH is equal to RH into BI upon D, where Hall coefficient RH is equal to, by rearranging above equation, we can write RH is equal to VH into D upon BI. If the value of RH is positive, then the type of semiconductor is P-type. Whereas if the RH is negative, the type of semiconductor is N-type. So from this equation, we can easily determine the type of semiconductor. Next is determination of charge carrier concentration. If you want to determine the charge carrier concentration, the value of Hall coefficient is equal to RH is equal to 1 upon NQ. Hence, charge carrier concentration, that is a small n, is equal to 1 upon RH into Q. If the value of RH is known, the charge carrier concentration can be found with the help of this equation. Now let's see the determination of charge carrier mobility. The electrical conductivity is given by sigma is equal to NQ mu, where mu is the mobility of charge carriers. Therefore, mu is equal to sigma upon NQ. As we know that RH is equal to 1 upon NQ, hence above equation we can write mu is equal to sigma into RH. Thus, the charge mobility can be determined using Hall coefficient using above equation. Now let's see problem solving, which is based on the Hall effect theory. First of all, first problem. The Hall coefficient of a specimen of a doped silicon is found to be 3.66 into 10 raised to minus 3 meter cube per coulomb. The resistivity of specimen is 8.93 ohm meter. Determine the mobility of the charge carriers. The solution of this problem is as follows. We have the given parameter, that is RH Hall coefficient, is equal to 3.66 into 10 raised to minus 3 meter cube per coulomb. and the resistivity of specimen is given, rho is equal to 8.93 ohm meter. Therefore, we can write conductivity, that is sigma, is equal to 1 upon rho, that is equal to 1 upon 8.93. We have the equation for the mobility, mu is equal to sigma into RH. So simply by putting the values of all these parameters in this equation, mu is equal to 1 upon 8.93 into 3.66 into 10 raised to minus 3. After calculating these values, we have mobility mu is equal to 0.4098 into 10 raised to minus 3 centimeter cube per volt second. So this is the answer of this numerical. Now let's see second example. A slab of silicon 2 cm in length, 1.5 cm wide and 2 mm thick is applied with magnetic field of 0.4 Tesla along its thickness. When a current of 75 ampere flows along the length, the voltage measured across its width is 0.81 millivolt. Calculate the concentration of mobile electrons in the silicon. The solution of this example is as follows. We have given parameters VH, that is Hall voltage, is equal to 0.81 millivolt, that is equal to 0.81 into 10 raised to minus 3 volt. The magnetic field capital B is equal to 0.4 Tesla. Current I is equal to 75 ampere. W width is 1.5 centimeter, that is equal to 1.5 into 10 raised to minus 2 meter. D is equal to 2 millimeter, that is 2 into 10 raised to minus 3 meter. Now we have equation Hall voltage VH is equal to 1 upon NQ into BI upon D. So rearranging this equation, small n is equal to 1 upon VH into BI upon D. That is the concentration of mobile electrons in silicon. So simply putting the values of all these parameters in this equation, we can write small n is equal to 1 upon 0.82 into 10 raised to minus 3 into 0.4 into 75 divided by 2 into 10 raised to minus 3. After calculating all these values, finally we have small n is equal to 1.851 into 10 raised to 7 electrons per meter cube. So this is the concentration of mobile electrons in the silicon slab. Now let's see example number 3. A copper specimen having length 1 meter, width 1 centimeter and thickness 1 millimeter is conducting a current of 1 ampere along its length. The specimen is kept in magnetic field of 1 Tesla along its thickness. It experiences Hall effect and Hall voltage 0.074 microvolt appears along its width. If the conductivity of copper is 5.8 into 10 raised to 7 per ohm meter, find the Hall coefficient and mobility of electrons in the specimen. So the solution of this numerical is as follows. We have given parameters. Small l is equal to 1 meter, small d is 1 centimeter, that is equal to 10 raised to minus 2 meter, t thickness 1 millimeter, that is equal to 10 raised to minus 3 meter. Then magnetic field capital B is equal to 1 Tesla and current I is equal to 1 ampere. Whereas the Hall voltage VH is equal to 0.074 into 10 raised to minus 6 volt. Sigma is equal to 5.8 into 10 raised to 7 per ohm meter. So we have all these given parameters. We have equation VH is equal to RH into BID upon capital A. So rearranging this equation, we can write for the Hall coefficient RH is equal to VH into A upon BID. Simply by putting all the values of all these parameters in this equation, we can write RH is equal to 0.074 into 10 raised to minus 6 into 10 raised to minus 2 into 10 raised to minus 3 divided by 1 into 1 into 10 raised to minus 2. After calculating all these values, we have Hall coefficient RH is equal to 0.074 into 10 raised to minus 9 meter cube per coulomb. Therefore, we have equation sigma is equal to mu upon RH. Rearranging this equation, we can write mu is equal to sigma into RH. By putting simply the values of all these parameters in this equation, we can write mu is equal to 5.8 into 10 raised to 7 into 0.074 into 10 raised to minus 9. Hence, the mobility of electrons in this specimen is mu is equal to 0.4292 into 10 raised to minus 2 meter square per whole second. So this is the answer of this problem. This is all about Hall effect. Thank you. Video in the description. The link of important information related to this video is given. Please go through it. Please like and share this video and subscribe to Dr. Khalkar's Classroom channel to get the notifications about my upcoming videos. Thank you.